Hello everyone, welcome back to Statistician's World. Today we're diving into one of the most misunderstood ideas in all of the data science projects, correlation versus causation. You have seen it already, right? Two things rise together and someone maybe says, aha, this causes that. But does it really? Let's find out why your model might be smart but for all the wrong reasons. So first, what exactly is correlation measuring? Correlation simply measures how two variables move together. When one goes up and the other tends to go up too, that's a positive correlation. But if one goes up and the other goes down, that's negative. And if there is no consistent pattern, correlation is near zero. So it doesn't say why they move together. It just says that they do move together. Let's make that more concrete with the most common measure, Pearson's correlation. Pearson's correlation, often called R, measures the strength and direction of a linear relationship between two continuous variables. Values near +1 mean a strong positive, near -1 mean a strong negative, and around 0 means no linear relation. But remember, it only catches linear patterns. Things like curves, jumps, or thresholds can fool it. Now, what if the relationship isn't linear? That's where Spearman correlation comes in. Spearman's correlation is smarter when data are not linear, but still move in one direction overall. So instead of comparing actual numbers, it ranks them first. But like for example, we have a data set of 1, 2, 5, 8, 15, and 75. It turns them into 1, 2, 3, 4, 5, 6. So outliers and nonlinear shapes matter less compared to Pearson correlation. And that's why Spearman's correlation is common in psychology, education, and anywhere that data aren't perfectly linear. So far, both Pearson and Spearman tells us how variables move together. But do they tell us that one causes the other? Not at all. Here is where people get it wrong. Let's see one of my favorite examples when people get correlation mistakenly equal with causation. In 2014, a Harvard Law student who was analyzing US data from 1999 to 2009 found out that as cheese consumption per person increased, death from people getting tangled in their bed sheets also increased. So mathematically, the two trends correlated very strongly, meaning that when one went up, the other did too. So does cheese cause fatal naps? Of course not. That's the classic trap. A third factor, like time, population growth, or coincidence, can make unrelated things move together. Now let's go deeper. How do we tell real causal effects from fake ones? Often there is a hidden or lurking variable that influences both. Say you see a correlation between ice cream sales and drowning incidents. In this situation, warmer weather is the real cause. It increases both swimming and ice cream sales. So that's why correlation alone can't prove causation. We need context, design, or experiments. And this misunderstanding doesn't just happen in the news, it happens in machine learning all the time. In ML, correlation traps are deadly. If your data has very strong correlations, your model will happily learn them and fail in the real world. For example, hospitals with more ICU nurses may have higher death rates, not because nurses cause death, but because they treat more severe cases. Unless you understand the causal structure, feature selection based on correlation can mislead your model. So be very careful with that. Now let's look at what good correlation analysis should include. Let's say you computed correlations and you have the results. But don't stop at the numbers. First, always visualize with scatter plots or heat maps, because numbers can hide nonlinear shapes. Second, check Pearson and Spearman side by side if the data may be skewed or ranked. And lastly, if you suspect a hidden variable, use partial correlation or multiple regression to control for it. The goal here is understanding, not just high R values. Speaking of visuals, let's talk about correlation matrices and what they really mean. Correlation matrices are great for spotting patterns, but be careful. Just because two features are highly correlated, it doesn't mean one explains the other. When selecting features, remember, high correlation between features causes multicollinearity, which is bad for models like regression, and high correlation between a feature and the target variable is a good start, but is still not a proof of causation. So my advice for you would be that treat correlation as a clue, not a conclusion. Let's put this all together in a small practical story. For example, a farmer noticed that every morning his rooster crowed and right after that the sun rose. So he thought, my rooster causes the sunrise. To make sure, he tried to test it. One day he kept the rooster inside and kept him silent, but the sun still rose. So he concluded that he was wrong. So that's the essence of causation. It's about what happens when you intervene, not just observe. Now for our machine learning models. Machine learning is great at correlation, but causation requires deeper design, experimentations, or domain logic. Let's wrap up with a short summary and see what's next. To sum up, correlation is a measure of movement, not cause. Pearson handles linear patterns, and Spearman works on ranks. And always visualize, check for hidden variables, and never assume cause from correlation. In the next episode, we'll look at sampling and bias, and we'll see how unbalanced data can quietly destroy model fairness and accuracy. And that was it. As always, thanks for watching. If this video helped you see correlation in a new light, like it, share it with your study group, and comment your favorite vicious correlation below. See you in the next episode.